The Earth's magnetic field is a fascinating phenomenon with profound implications for life on the planet, our understanding of geology, and even futuristic energy applications. However, misconceptions about its power and utility often cloud the discussion. This video unpacks the Earth's magnetic field, its behavior, and whether it can provide us with free electricity or insights into planetary and galactic processes. The Earth's magnetic field, generated by the motion of liquid iron in its outer core, is a crucial shield for the planet. Measuring approximately 50 microteslas at the surface, it protects us from harmful cosmic and solar radiation and helps retain our atmosphere. It also provides a navigational aid for humans and animals alike. Earth's magnetic poles are not fixed. Over geological time, the field undergoes reversals where the north and south magnetic poles switch places. Evidence from ancient rocks and sediments shows these reversals happen irregularly, roughly every 200,000 to 300,000 years, though the last one occurred 780,000 years ago. Contrary to popular fears, there is no direct evidence linking magnetic pole reversals to mass extinctions or catastrophic biological effects. The magnetic field deflects solar winds, streams of charged particles emitted by the sun. Without this shield, the Earth's atmosphere would be gradually stripped away. This fate befell Mars, which lost its magnetic field billions of years ago, exposing it to atmospheric erosion by solar winds. Mars's smaller size caused its core to cool and solidify more rapidly than Earth's. This halted the dynamo mechanism that once generated its magnetic field. Evidence of Mars's ancient field comes from fossilized magnetic anomalies in its crust, particularly in the southern hemisphere, which also hint at magnetic pole reversals during its active period. Mars's lack of a magnetic field presents challenges for human colonization. Without this protective shield, the Martian surface is bombarded by radiation and micrometeorites. Furthermore, efforts to rebuild Mars's atmosphere by releasing gases would likely fail in the long term, as solar winds would strip away any recreated atmosphere. Mars's thin atmosphere provides limited protection from meteorites. Unlike Earth, where the atmosphere burns up small meteoroids, Martian explorers face a slightly increased risk of meteorite impacts. However, the likelihood of being struck remains extremely low even on Mars. Magnetic fields and galactic scale phenomena. Faraday's law of electromagnetic induction explains that changing magnetic fields induce electric currents in conductive materials. This principle is central to understanding whether planetary or galactic magnetic fields can generate significant electric currents. On small scales, such as a coil of wire, this effect is practical and well documented. On planetary or galactic scales, however, several constraints make it unlikely. The Earth's magnetic field changes very slowly over time, generating negligible currents. Intergalactic space is a poor conductor, limiting current flow even if magnetic fields change. Galaxies have large-scale magnetic fields, though they are much weaker than planetary fields. These fields interact with cosmic plasma, shaping phenomena like galactic jets and the cosmic web. Changes in galactic magnetic fields can induce currents in interstellar plasma, but these are diffuse and limited by the vast distances and low conductivity of space. While it is theoretically possible to generate electricity from the Earth's magnetic field, the practical challenges are significant. Let's evaluate potential methods. A changing magnetic field induces a current in a conductor. The amount of induced electricity depends on 1. The strength of the magnetic field, 2. The rate of change of the field, and 3. The size and conductivity of the conductor. The Earth's magnetic field is relatively stable, with changes occurring on geological timescales. This slow variation results in minimal current generation. At 50 microteslas, the field is far weaker than those produced by household magnets or industrial electromagnets, limiting its utility. Harvesting electricity would require significant motion of conductors relative to the magnetic field, consuming more energy than it generates. While large-scale power generation is impractical, there are niche applications. Moving conductors such as vehicles like trains or ships moving through the magnetic field could induce small currents, though these are not commercially viable. During geomagnetic storms, fluctuations in the field can induce larger currents in long conductive structures like power lines. However, these effects are generally destructive. In space applications, electrodynamic tethers could harness the interaction between a moving conductor and Earth's field for propulsion or power generation. The Earth's magnetic field pales in comparison to artificial magnetic fields. A refrigerator magnet produces around 5 milliteslas, 100 times stronger than the Earth's field. MRI machines can generate fields up to 3 teslas, far surpassing planetary fields. Harnessing artificial fields for electricity is far more efficient than relying on the weak and slow variations of Earth's natural magnetic field. The Earth's magnetic field is vital for life and understanding planetary and cosmic processes. While it shields us from radiation and contributes to phenomena like auroras, it is not a practical source of free electricity. The weak, largely static nature of the field limits its utility for power generation. Efforts to harness it would be overshadowed by more accessible and efficient renewable energy sources like solar or wind power. On a larger scale, magnetic fields play an essential role in shaping the universe's structure, driving processes in galaxies and interstellar space. However, harnessing these phenomena for human use remains the domain of theoretical exploration. In the quest for sustainable energy, focusing on well-established renewable sources is far more promising than attempting to exploit the Earth's magnetic field. Still, the study of magnetism continues to unlock secrets about our planet and the cosmos, expanding the boundaries of science and imagination. If you like this video, don't forget to like and subscribe. Share it with others thirsty for knowledge. Thank you for watching.